Let's have a look at what we might call here some gate equivalence. Okay, so gate equivalence. All right. Now, what I'm going to do here is use basically De Morgan's theorem. So look, let's just take that NAND gate as an example. All right. So here's a NAND gate sitting here. Okay, 1, 2, 3 inputs. All right. Let's say these are A, B, and C inputs. We know the output is what? A, B, C, bar over the whole thing. Now, if I use De Morgan's theorem on this, you remember De Morgan's theorem? And if you don't, please pause the tape at this point and have a look at De Morgan's theorem. De Morgan's theorem would allow us, what? To basically represent this as A bar, or B bar, or C bar. So really, I could say an equivalent to this NAND gate could be what? Well, you could say it looks like an OR gate, doesn't it? With what? Inverted inputs. And so, if you like, bubbled inputs like so, where this, of course, would be A, B, and C. All right? Let's do the same thing with our NOR gate. All right, so here's our NOR gate. We'll look at it right here. Okay? Let's have 3 inputs again, A, B, C. Let's look at the output, which would be what? A, or B, or C, bar over the whole thing. Using De Morgan's theorem then, on this, that is equivalent to what? A, bar, B, bar, C, bar. Okay, so then a gate equivalent of this NOR gate, could be what? It could be really an AND function with inverted inputs. And so we could draw that then as an AND gate with bubbled or inverted inputs, such that this is A, this is B, and this is C. Okay? All right. Let's look at another example here. And what I want to look at really is, if you like, an AND/OR implementation or an AND/OR function. Okay? All right. Now here I have basically 2 AND gates and OR gates, so I have, if you like, an AND/OR implementation. So the output of this AND gate is what? AB. The output of this AND gate here is CD, and I'm ORing these 2 product terms together. So the function then is AB or CD. Let's have a look at this NAND gate circuit over here. I've got AB. What's the output over here? This would be what? AB with a bar over it. It's the output of this NAND gate. It would be what? CD, if you like, with a bar over it. Okay, so what's the output over here? Yes, it would be what? AB bar ANDed with CD bar. We want the NAND of it, so a bar over the whole thing. Now, could I apply De Morgan's theorem to this? I could get rid of this bar here if I applied De Morgan's theorem, couldn't I? And if I do that, then I have what? AB bar bar or CD bar bar. And what is that equal to? That's just simply equal to AB or CD. So really, these NAND gates then in this configuration represent an AND/OR function. Now look, using that gate equivalent approach, let's think about that a second. I'm going to redraw that circuit. Okay, so here I've got a NAND gate. Here is A, B feeding into that NAND gate. Here I've got another NAND gate, and I've got what? CD feeding into this. Now look, what's the gate equivalent here of a NAND function? Do you remember what that was? We just did that a moment ago. What was the gate equivalent of that? Yeah, the gate equivalent was what? It's an OR gate, isn't it? With inverted inputs. So why don't we just draw that gate equivalent down like so? There it is, it's an OR gate with inverted inputs. Okay, and let's connect like so and connect like so. Now this approach here makes this logic very readable because look, this bubble cancels with this bubble cancels with this, and what have we got? We've got an AND/OR function, and so F is equal to AB or CD, okay, an AND/OR function. When one is designing and looking at NAND implementation, often in schematic entry programs, you have an option of representing your NAND gate in this fashion, okay, or you have a choice of representing this as being your NAND gate. And so you can now draw your logic and make it, as it were, very readable in this form. Okay? Okay, now let us review KMaps or Karnaugh maps, KMaps being the abbreviation. Okay? Now, KMaps are really figures on which Boolean equations can be plotted. And KMaps are actually arranged so that basically terms, product terms, only differ by a single variable. Okay? Let's look at this. All right? This is a two-variable KMap sitting here. Okay. This product term sitting here, this is A and B variables. This product term sitting here would be what? This would be A bar, B bar. Okay? This product term sitting here would be what? The 0 here is an indicator of the A bar, and the 1 here is an indicator of B. So this term here would be what? A bar B. What's this term here? Well, the A is, as it were, a 1, so that's an indicator of A. So this would be A, and this would be B bar. And then this term here would be just simply AB. Now, in some of the problems which I give you, in fact, in the first digital lab, I actually give you a Boolean equation and ask you to minimize it and then build the circuit. I actually give you the Boolean equation as a sum of product terms, and each one of those product terms I just define by its decimal equivalent. Okay, so you could represent that on a map as well. Remember, where this is a product term, product term, product term, product term, and I could say, look, AB. Now, if I treat A as the most significant, so A is, if you like, the most significant bit, and B, if you like, is the least significant bit. Okay, and that's just the way I'm representing this. And I talk about the decimal equivalent of those product terms. Then I can say, okay, when we have 0, 0 for A and B, the decimal equivalent is 0. I have 0, 1, the decimal equivalent is 1. And then I have 1, 0, decimal equivalent being 2. And then 1, 1, decimal equivalent being 3. Okay? And so, as I say, sometimes I give you a function, and I say that function is really like a summation of product terms, and the product terms could be 0, let's say 2, and 3. And I could say, okay, given the problem in this form, see if you could minimize it. So what does it mean? It means plot on the map each one of these product terms. So the 0 corresponds to what? A bar, B bar, the 2 corresponds to A, B bar, and the 3 corresponds to AB. All right? So each of these squares then has, if you like, a decimal equivalent. And what would those be? Well, look, this is 0, 0. This would correspond to decimal 0. This is 0, 1. This is our decimal 1 sitting here. And then this is 1, 0. So that's 2, decimal 2. And then, of course, this guy over here is the decimal 3 equivalent. Okay? And so if I were plotting this function on this map, I would say I have a product term there. I have a product term there, and I have a product term there. Could I now minimize and then implement that Boolean equation? Okay? All right, that's a two-variable map. Let's now consider a three-variable map. Okay, here is a three-variable map, okay? And once again, I'm considering A, most significant, and C, the least significant bit, okay? All right, so what would this product term here be? All right, well, look at this. This would be what? A bar, B bar, C bar, okay? Let's take another example. What would this product term here be? Well, look, A is 1, so that's A. B is what? 1, so that's B, C bar. What's this product term? This would simply be A, B, C. All right? Now, why don't you fill in this completely? Oh, look, I'll do one more. What about this product term here? This is A bar, B, C bar, okay? Now, once again, each one of these squares has, if you like, a decimal equivalent, just as we looked at before with the two-variable map. And once again, you could have a look at this and verify what I'm saying. All right, so this square is 0, 0, 0, corresponds to a decimal equivalent of 0. This is 0, 0, 1, so this is decimal equivalent 1. This is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. Okay, so please maybe pause at this point and just go ahead and verify that for yourself. All right? Now let's look at a 4-variable map here. Now remember, in my case, I'm assuming A is most significant, D is least significant. Okay, so A, B, C, D. D is least significant, A is the most significant product term. Okay, or bit, I should say, or variable. Okay, so what's this square here? All right, that's A bar, B bar, C bar, and what? D bar. Okay, that's that square there. You could go ahead and fill in each one of these squares. This square here would be what? A, B, C, D. That's that product term right there. Okay? Once again, I can talk about decimal equivalents for each one of these product terms. Of course, this would be 0, this would be 1, and please verify this for yourself. This would be 2, and this would be 3. This would be 4, this would be 5, this is 6, 7, and then 8, and then 9, 10, 11, okay, 12, 13, and then 14 and 15. But again, you need to sit down, maybe pause at this stage and verify that for yourself, okay? It's important that you do that. Okay, this is a 5-variable map. Now look, we wouldn't really go beyond 5 variables. You can, but really there's no real purpose in actually doing that, any minimization beyond that. And you're really going to use a minimization program as opposed to hand minimization such as this using KMaps, okay? All right, 5-variable map. All right, well, look, let's put in our variables here. This is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Again over here, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1, 0. This would be the E equals 0 map, and this is the E equals 1 map. And we're looking at product terms, what? A, B, C, D, E, okay? So A is what? The most significant bit, and we're saying that E is the least significant bit, okay? There are other ways to draw these maps. It's the understanding of what we're doing here that is important, okay? So what is this square right here, okay? If I look, and I'll write it off to the side over here, what is that product term? That product term would be what? It would be A bar, B bar, C bar, D bar. It's on the E bar map, E bar, okay? That's that particular product term there. Okay, we could take another example. Let me take that product term sitting right there. What would that be? Well, it would be A, B, C, D, E. So it's the A, B, C, D, E product term over there. Okay, now once again, we can look at the decimal, if you like, equivalent of each one of those product terms. And really your first lab actually requires you to look at a 5-variable map. Okay, to minimize and then build. Okay. Okay, once again, here is our 5-variable map, and now really what I want you to do at this point is identify, as I say, the decimal equivalent for each one of the product terms. Okay. Again, A is most significant and E is really the least significant. Okay, so look at this. 0, 0, 0, 0, 0. Of course, that would correspond to what? Decimal 0 at that point. Okay. What about the square here? That would be what? That's 0, 0, 0, 1, 0. Okay? What is that decimally? 0, 0, 0, 1, 0. Yeah, that would be 2, wouldn't it? So that's the decimal 2 square. Okay? What about the square over here? What's that? 0, 0, 1, 0, 0. Yep, that's the decimal 4. Okay? What about this guy? 0, 0, 1, 1, 0. Okay, what is that? Yep, that's the decimal 6 square sitting there. Let's go over to this map, okay? What is this square here? 0, 0, 0, 0, 1. Yeah, it's easy. Decimal 1, isn't it? This square here, 0, 0, 0, 1, 1. Yep, that's 3, isn't it? And then this square over here, which would be 0, 0, 1, 0, 1. Yes, that's 5. Okay, and then finally we'll do this one, 0, 0, 1, 1, 1. Yeah, that's 7. Okay, so what I want you to do, once you complete, identify each one of these squares with its decimal equivalent. All right, so let's see if you can do that. Okay, look, let's take a break at this point, and look, when we come back, we'll consider, as a review, plotting and minimizing Boolean functions using KMaps. All right?